Well, welcome to our question today where we're asking ourselves, is it possible, just by looking at compounds, to predict whether or not they will affect the pH of water? You're often asked in chemistry or science to make predictions, and so it's an important skill to learn, and if you're studying chemistry at school or maybe university, you'll often get these prediction questions. Now, I'm drawing a familiar shape right now. You may recognize it as a castle, or hopefully more likely the periodic table. I'm going to color in one side of it red. There it is. And hopefully you can recognize that the middle left of the periodic table are where you can find the metals. Now, the metals, if for example we might zoom in on this area of the periodic table, you may find a common metal called magnesium. We're just going to use magnesium as our example for our question. Remember, we're trying to ask ourselves, just by looking at a compound, is it possible to predict some of its behavior in terms of pH? Well, what we're going to look at today are things called oxides. Now, oxygen can be found over on this side of the periodic table. Why is it on this side? Well, it's a non-metal, which means it's not like magnesium, and so it's grouped in a different area of the periodic table. It would be grouped in group 6, which means that oxygen has 6 outer shell electrons. So I'm just going to put them on here with some dots, which is one of the ways we represent electrons in chemistry. Now, in the history of chemistry, it was common that as all these different metals began to be understood and isolated from the Earth's crust, they were normally found as oxides, as compounds. And this was confusing to chemists because they realized that all the metals, pretty much, except for gold and platinum and different other very stable metals, they all tended to be rather annoyingly found as a compound, which was not usable as a pure metal until they worked out how to extract the metal from the oxygen. So oxides are one of the most common ways that we find all of these various elements in the Earth's crust. So it's important to look at oxides as a class of compounds. In the early days, chemists actually called the reaction between a metal and oxygen oxidation because oxygen always seemed to be involved. Now, oxygen is a very common element. It makes up, this is molecular oxygen, approximately 18 to 20% of the gas in our atmosphere. And of course, we're used to seeing oxygen written as O2. So O2 is really everywhere on the surface of the Earth, so if it's always going to react with metals, it makes sense that oxides of metals are everywhere as well. Now, the way that we tend to draw O2 is in this way. You're probably familiar with seeing this. We're here circling some electron shared pairs. Oxygen, of course, wants to have 8 electrons around each atom. This is the Octet Rule. 8 electrons mean that something is stable. It's the driving force of most chemical reactions. If we circle these ones, we're saying that all the electrons here are shared by this atom and by this atom. So if you count them up, 1, 2, 3, 4, 5, 6, 7, 8, this atom thinks it has 8. 1, 2, 3, 4, 5, 6, 7, 8, this atom also thinks it has 8. So molecular oxygen, O2, is a stable form of oxygen, and it's the form that our bodies need to respire and survive. But I want you to think about sharing for a minute. No one really likes to share. If you're a teenager, you probably don't like sharing, and if you're an adult, you probably don't really like sharing either. So oxygen's a bit like a teenager or an adult. It doesn't like to share. If it has to, it will, but in the end, if it can have its own electrons, it would far rather have its own electrons. This is the driving force behind why oxides are so common. If oxygen is everywhere, and it would rather have some electrons, then perhaps it's going to form a new type of oxygen, an oxide. All it needs is its own electrons. So imagine if I had 2 spare electrons. I could offer them to this oxygen part of the oxygen molecule, and it might say, you know what, I'll have those, so let's put them on. Suddenly, this atom has 1, 2, 3, 4, 5, 6, 7, 8 of its own electrons and no longer needs to share here. If I could bring in 2 lots of 2 electrons, the same could happen for this one too. 1, 2, let's put 2 on, 3, 4, 5, 6, 7, 8. So sharing is no longer required. So suddenly oxygen is able to form something called an oxide. So let's take a look at how that works. O2 plus 4 electrons can actually produce 2 individual oxide ions. It's now 2 minus because it has gained 2 negative particles, which means it now has 2 more electrons than protons in the nucleus, so it takes on a 2 minus charge. Our question, of course, is, well, where can we get these electrons from? Where on earth might they come from? The answer is the metal that was involved in the formation of the oxide. Magnesium is our case study today, so let's have a little bit of a closer look at magnesium now. Remember, I said that you could find magnesium on this side of the periodic table. This particular part of the periodic table is called group 2. Why? Because magnesium has 2 electrons in the outer shell. There they are, and let's bring it down here. So magnesium, if you could possibly get it, you might find it in your lab as a piece of magnesium ribbon, it could have 2 electrons in the outer shell, but you know what? Magnesium would prefer to have 8. Now again, dare I go back to teenagers? I love teenagers, but anyway, we'll talk about them. Magnesium is a little bit lazy as well. It asks itself a question. In order to get to 8, if I have 2, I would need to find 6 more electrons, or I could simply just get rid of 2. The smallest amount of work would be to just get rid of 2. Finding 6 more sounds like far too much work for our teenager magnesium. So in the end, magnesium says, I will just happily lose 2 electrons. So we can show this in the following way. Those electrons are here. In order to get rid of them, magnesium can make a compromise. Out come the electrons, so now we're going to say here they are. What we're saying by this plus sign is that those 2 have now come off magnesium, so we now have a magnesium ion and 2 electrons. And because it lost 2 negative particles, it has become a charged ion, 2+. And that's what tends to happen spontaneously. Magnesium being a metal in the periodic table, remember the further left you move across the periodic table, the more reactive you are. Magnesium as a moderately reactive metal loses those outer shell electrons very readily. So you tend to not find magnesium in this form. You nearly always find magnesium in this form with a 2+ charge, having lost its 2 electrons. So now we've found the source for the electrons that oxygen would like and where they have come from on the metal. So now let's think about this. Magnesium, having become a charged ion with a magnitude of 2+, of course, is now electrostatically attracted to the oxygen ion that became 2-. You can see obviously that opposites attract and you're going to form magnesium oxide. Now that answers the question as to why we would wish to predict how this might affect pH, because you can see that this happens spontaneously. Wherever you find oxygen, the metals will tend to lose their electrons to end up with a full outer shell of 8 electrons, and therefore they become charged and they stick, if you like, to the oxide ion. Wow! So that would mean, if you wanted to make a prediction, that maybe oxides of metals are very common, and you would be correct. For example, iron, that's a transition metal, we could write him in here somewhere, this is where the transitions live. Iron, which can form 2+ or 3+, we'll put 3+. Those 3 electrons that used to be on iron, they left a long time ago and they've ended up on oxygen, and iron will form iron oxide, which of course we all recognise as that horrible rust that we try and eradicate from our metals. So it's very common, nearly all the metals in the periodic table form oxides readily. But our question is it possible to predict how they behave in terms of pH? In order to answer that question, you're going to have to watch the next video.